So for the removable discontinuities, whenever you have a graph, these are places where you have a hole in the graph. Okay? Yes. Uh-oh. Michaela, did you have a extra? Did anybody have an extra somewhere? There we go. Okay. So, holes are called removable discontinuities because you can fix them by putting one single point back there. So if we just added one point right here, it would fix the whole entire graph, right? And it would be continuous the whole way. So those are removable discontinuities. Some non-removable discontinuities are jumps. Jumps are typically going to happen with piecewise functions. So that's like when you got different pieces of a function together. So you might have something like this, and then it might jump up here and do something like that. So your removable discontinuity, right, non-removable discontinuity right here would be a jump occurring at that point. And then you also may have vertical asymptotes. You also may have vertical asymptotes, and at a vertical asymptote, it can look a few different ways, but you will have like a, let me use a different color there. This vertical line is not part of our graph, but the graph is the blue line, and it might do something like this, or it could do like this, or it might do both. But you have your y values approaching positive or negative infinity as you get closer and closer and closer to that x value. Okay, so these are the three types we're going to be concerned with finding. Today we're just going to look at finding these discontinuities, understanding where they're at. Tomorrow we're going to start proving that there are discontinuities, which we have to be a little bit more formal about. So there are several things that can cause a discontinuity. You could have negatives under a square root or any even root, so like a 4th root, a 6th root, 8th root there. That's going to cause a discontinuity. A 0 in the denominator of a fraction, that's going to be the one we're going to look at the most today. A number less than or equal to 0 inside of a log. Okay, you can't have anything you take the log of has to be a positive number, so that's going to cause discontinuities. A piecewise function that has a hole or a jump, that we're going to be looking at today. And then some trig functions, like for example, tangent. Does anybody remember what tangent looked like when we graphed it? Yeah, it was like this, like squiggle. I got a good joke back there on my board. The girl with the bikini on, and she's got her tan lines are showing, and she's got the tangent graph there. There's actually a lot of good tangent jokes. I got a few more I need to print off and put up there. The internet, the algorithm just keeps giving them to me these days because it's figured out the things that I like. But they're definitely vertical asymptotes on those graphs. So, the main two things we're going to be looking at are going to be rational functions, which are fractions, and piecewise functions. Those are the big two that we really need to know how to find discontinuities for. So, for example 1, they're telling us we got to find any x values for which x is discontinuous. Tell whether the function is removable or non-removable. Okay, so here, does anybody remember what we need to do if we have a fraction like this and we're looking for holes or vertical asymptotes? What? Factor. Yeah, and also the top if we could, we can't factor the top on this one, right? So we're going to factor. To factor that one, Avit, what would you do first? You can do it. You can do it that way. But if there is a greatest common factor, that is going to be what you want to do first. Do we have a greatest common factor on this one? We do. So we're going to pull the 2 out. It also avoids having to do that, like, sort of little bit more complicated factoring. You could do that first, but you're still going to have a GCF. You got to pull out of one of your factors. Okay, then we could factor the denominator further. And so a lot of you, I think, use the X method. You got your multiply to get -6, add to get +1. What numbers work for that? +3 -2 right there. Okay, and I didn't really leave enough room right here. But discontinuities in these types of functions come from the denominator. So I definitely have 2 discontinuities. One of them is x equals -3, and the other is x equals +2, right? We're just looking at these 2 right here. We got opposite signs. What about that 2? Does it do anything? Is 2 going to equal 0 at all? Because what you're doing right there is you're saying like 2 equals 0, x plus 3 equals 0, and x minus 2 equals 0. You're trying to think of the things that would give you 0 in the bottom. Does 2 equal 0? No, there's no answers that come for it. What about if there was an x there? What if I had 2x equals 0? Then you would get a value, but we don't have an x for this one. So definitely I have discontinuities at -3 and at 2. Does anybody remember how I can tell whether they're removable or non-removable? Whether we got a hole, or for these it's going to be a vertical asymptote if it's non-removable. Okay, if your factor cancels out, so your x plus 3's can cancel here, that means you have a hole there, or a removable, and then vertical asymptote at 2. And if I had room, I might write removable out next to the hole and non-removable next to vertical asymptote, but I really did not leave enough room on this page. Okay, so if we do the next one, we would need to factor here. And numerator, this one's going to be x plus 2, x plus 3. And the denominator will have x plus 3, x plus 1. So our answers, again, come from the denominator. Not the numerator, but the denominator. So we got x equals -3 and x equals -1. Let's see. Matthew, at x equals -3, do I have a hole or a vertical asymptote? That one's a hole because x plus 3 and x plus 3 will cancel out. And then Michael, at -1, vertical asymptote, because we have a value that does not cancel out. -2 is not a discontinuity. Anybody remember what -2 is? It is a 0 of the function. It's an x-intercept of that function. So x-intercepts come from the top, but this question is not asking us about that, so we only look at the bottom. The only reason we even care about the top is to see if it factors and cancels. If they only asked for discontinuities and didn't ask you to like classify them, you could just factor the bottom and be done there. All right, so let's look at a few more. Okay, so you had one of these similar to number 3. It was a limit problem instead of this, but you had one similar to number 3 on that limit activity with the cards that we did. It was like, that one was like absolute value of x over x or something like that. And this is similar. These almost cancel out, but they really can't cancel out because of that absolute value bar, right? So let's pretend we can't use a calculator on this. Let's think it through first, and then we'll graph it to see if we're right. Let's just make us like a table here. So, first of all, where are we going to have a discontinuity? We are going to have a discontinuity at x equals -1. The question is it a hole? Is it a vertical asymptote? Is it a jump? There. So we're definitely going to have x equals -1 as discontinuity. If you plug in -1, you're going to get 0 over 0, which does not tell you the answer to the problem. So let's think about sort of values close to -1. -1's the problem. We should get answers everywhere else. So maybe I'll start like lower than -1. So maybe I'll plug in like -3. Okay. If I plug in -3, I have absolute value of -3 plus 1 over -3 plus 1. That is going to give me absolute value of -2 over -2. What is absolute value of -2? Positive 2 over -2. What do I get? -1. Okay. What about if I've got -2? Plug in -2. I would have absolute value of -2 plus 1 over -2 plus 1. That's going to give me absolute value of -1 over -1. That is positive 1 over -1, and I get -1 again. I can't plug in -1, that doesn't work, so let's just maybe like a -1.5, right? Almost like we're doing a limit here. So that's going to give me -1.5 plus 1 is -0.5 over -0.5. That's going to give me positive 0.5 over -0.5. What do I get? -1 again, right? So, are you seeing a trend start to happen here? What do you think we're going to get for any number less than -1 that we plug in? Looks like it's going to be -1, right? No matter what number we plug in. Question is, do we get the same if we plug in numbers bigger than -1? Like if I plug in, like let's say I plug in 2. So to do that, I would have absolute value of 2 plus 1 over 2 plus 1. That'd give me absolute value of 3 over 3. It's 3 over 3. And what does that give me? Positive 1. Okay, will anything change if I plug in 1? I mean, the work will change, but will I get a different answer? I'll have 1 plus 1 over 1 plus 1. I'll get 1 for that also. If I plug in 0, I'd get 1 over 1. Still 1. If I plug in -0.5, I'm still going to get 1, right? So what looks like's happening here is I get -1 all the way up till I get to 1 from one side, but I get positive 1 from the other. What does that sound like it's going to look like on the graph? A jump. It's going to jump up one to the other. Let's graph it on Desmos to see if our conclusion is correct. So if I graph y equals absolute value of x plus 1 over x plus 1. That is exactly what we have, right? A jump in the graph like that. So this x equals 1, we wrote right here as our answer. That is going to be a jump, or we could call it non-removable. And that's our discontinuity. So, in order to keep us from having to do that table every single time, we should be making a mental note here. This is going to happen anytime you have something that would cancel, but one of them has absolute value bars. So if you have absolute value bars on one and no absolute value bars on the other, that causes a jump in the graph. What you're going to have is just like horizontal lines at 1 and -1, and they are going to take a jump wherever your denominator would equal 0 for that. Okay, so if you see more problems like that, you don't have to go all the way through this work again. You can just say there's a jump at that point. Does that make sense? Okay. 4 asks us for f of g of x, and then they give us f of x and g of x. So we could see, we could look at each individually. Are you going to have a discontinuity on f of x? Is there anywhere the denominator equals 0? Yes. Where is it? -2. Okay. So f of x itself has a discontinuity at -2. What about g of x? Do we have any discontinuities on g of x? No, it's just x squared plus 3. When you get to your homework assignment tonight, there's a few problems like this that are just like parabolas or a sine function. Do those have discontinuities? No, they're smooth curves the whole time. So the answer is none on that. But kids always ask me about those because it seems like that shouldn't be the answer. So G does not have a discontinuity. The question here is, what about when you put them together? So if I have f of g of x, then f of g of x means that I should take g and I should plug it into f. So that will be 1 over x squared plus 3 plus 2. And if I simplify that, I've got 1 over x squared plus 5. Okay, does this have a discontinuity? I've got a denominator, right? It might not be the same number. Right, like we plug any numbers in, right? When I square this, what kind of number do I get? Positive, no matter what number I plugged in, right? As long as it's a real number. And then I add 5 to it. Could it possibly equal 0 by doing that? A positive number plus 5 is always going to be positive, right? So this has no discontinuities. Even though f does have a discontinuity by itself, f of g of x does not have a discontinuity. Another thing you can do that will like alert you to the problem is what we usually want to see is we want to see if the denominator equals 0, right? So if you do x squared plus 5 equals 0, you would have to subtract 5. There, x squared would equal -5. Then what would you do to get rid of the square? Square root, but why is that not good? You can't take the square root of a negative number unless you use a I, which is an imaginary number. So this does have some like imaginary like issues there, but we're not concerned with that. We want real numbers. We're talking about a graph. Imaginary things do not show up on the graph. So we would say for this one that we just have none. And if you recognize, like Michael did, hey, you're squaring something, then you're adding another number to it, that always has to be positive. So that you don't even have to set up like x squared plus 5 equals 0. Okay. Okay, questions here? All right. Next, let's move to some piecewise. Okay. With piecewise, you first want to think about each individual piece and see if each piece has a discontinuity. X divided by 2, what's that look like? If we graphed it, what's it going to look like? If I wrote it a different way, I think you'd be able to tell me. What if I wrote it as y equals 1/2 x? Okay, that's equivalent. It's just a straight, it's a slanted straight line, right? Not a horizontal line, but it's a line. Is that always continuous lines? Yes. So no issues there. Absolute value bars. What do those graphs look like? They're V shapes. Unless they're like shifted, they're always going to be positive. Are they discontinuous anywhere? No, they're continuous everywhere, so that's fine. Square root of x plus 1. Now, it does have an issue, right? Because what can we not have with square roots? Can't have negatives under the square root, which tells me x plus 1 has to be greater than 0, right? So if I subtract that 1, x has to be greater than -1. But look at your condition. Are we using it where x is less than -1 anywhere? No. X is greater than or equal to 3, so are we going to have any discontinuities for this part? No. Most of the time, you don't have discontinuities in the pieces. It can happen, but most of the time, they're fine. So our next question is, do these match up, right? So I need to know if these are going to match up. Now, I'm going to use some limit notation here because what we're going to do tomorrow is going to require us to use limit notation. So, first thing I'm going to look at is my -5. I need to look at these two functions at -5. The proper way to write this is to write the limit as x approaches -5 from the left. We're going to put the negative behind it of f of x. Thank you. And then from the left, I can live with it if you do not write this step, but I'm going to write it to be extra clear. From the left side, which equation are we using? Top, middle, or bottom? Top. Because if we graph this, unless they did something crazy on the piecewise function, they generally put the left piece first, middle piece last, the right piece, right? They go from left to right. There. And so it's going to be x over 2. Almost all of these are going to be direct substitution problems. I just plug in -5 over 2. And that's what I get, -5 over 2. Then I want to do the limit as x approaches -5 from the right. That really shouldn't be there. Of f of x. Okay, which we're going to use which function for that one? Top, middle, bottom. Not bottom, because it's the ones that involve -5, right? Does the bottom one have anything to do with -5? No. So we're going to use the middle one, right? So that's going to be absolute value of x minus 1. So I'm going to plug in -5. Oops. That's ugly. Right there, it's a -1. That's going to give me absolute value of -6. What is the absolute value of -6? 6. Okay, so my limit from the left is -5 over 2. My limit from the right is 6. What's going to be going on right here? What's that graph going to look like? It's going to be some sort of jump, right? Because those two don't match. So I could say at x equals -5, I have a jump, which is a non-removable. So that is one discontinuity. Questions there? But I've got another place I got to check. What other number do I have to check? I got to check at the 3. Now, what two pieces of this piecewise function do I need to consider at 3? Middle and bottom, right? The top has nothing to do with 3, so I'm ignoring it for this one. I would say the limit as x approaches 3 from the left of f of x. It's going to be the limit as x approaches 3 from the left of absolute value of x minus 1. The left one will be the middle one here. And that is going to be absolute value of 3 minus 1, which is going to be 2. I know you could just like plug this in your head without writing that limit notation, but it's really going to help us with what we got to do tomorrow. And then limit as x approaches 3 from the right of f of x. We would use the bottom one for that, so square root of x plus 1. And so we'll plug in our 3. Square root of 3 plus 1 is the square root of 4, which is 2. Now, I'm getting the same thing from both sides here. You do need to check and make sure that one of them is a less than and the other is a greater than or equal to. One of them needs to have the or equal to with it. If they're both less thans and greater thans, then you're without the or equal to, then you have a hole in the graph because they're both open circles. But most of the time they are not. These match up. We're going to see tomorrow if we're proving continuity. There's one more thing we'd have to do. But our graph, since we're getting the same numbers right there, we're not going to have a discontinuity at 3. It's -5 is our only one. But you got to check because it could end up being the same or different. Does that make sense? Okay. Let's do one more of these. I think one more. Yeah, and 7's a little bit different. All right, for example 6. Am I going to have a discontinuity for cosine x minus 1 over x? Can I have a 0 in that denominator? Michael's saying no. It could be 0, but do you have a reason you're saying no? It's not less than or equal to 0. So 0 would make this have a discontinuity, but this one's not defined at 0, right? It's only numbers less than 0. So we don't have a discontinuity within the function here. 5x is just a line. We don't have a discontinuity there. 0 is where we've got to check, right? So I think I did skip some trig stuff. We can do this the way I showed you the other day, though. We got limit as x approaches 0 from the left of f of x. From the left, which function are we using? Top function or bottom function? Top. So we got cosine x minus 1 over x. Now, if I plug in 0 right here, I get 0 over 0, right? Cosine of 0 is 1. 1 minus 1 is 0. We'll get a 0 in the bottom, too. So if I plug in 0, I am going to get 0 here. So this one's harder because we have to actually solve the limit. Any ideas on this one? It is a little bit like yesterday's warm-up. I really want like 1 minus cosine squared x. That might be helpful to us. Actually, is it like yesterday's warm-up? Because I don't sign the bottom. Actually, it may not be. I think I skipped something somewhere. I think there were some notes that I did not do the trig stuff that I was supposed to. All right. I think I've skipped some. I need to go back and look through. But for tonight, if you see some trig like this, and it's not like just a plug, some of them will just be you can plug in the number. This one you cannot just plug in the number. I will allow you to use Desmos if you run into trig like this because I think I have skipped something. So if I graph cosine x minus 1 over this whole thing over x, and we're doing x approaches 0, what's our answer going to be? What? If we're talking about limit, so the value is undefined, but if we're doing a limit, zero, okay? Because the function is undefined there, but can you still have a limit at a hole in the graph? You can't. Limits are what you're getting closer and closer and closer to, even if you don't touch it, right? So when I look at this graph, right here at 0, I do have a hole in the graph, but both sides are going to that same spot, right? So the answer that we would get there would be 0 for that limit. Oh, that's the wrong thing. So we would get 0. I need to go back and show you a couple things algebraically on that trig stuff. But for now, we're just going to use the graph. If I do the limit as x approaches 0 from the right of f of x, this one will be much easier. Of 5x. That's going to be 5 times 0, and that is going to be 0. I do have an or equal to with one of these, and it is the one that will be defined. This one would not be defined at 0, right? This one would be. I do have an or equal to with one of these. So do I have any discontinuities here? Those two match up. I would say none for this. You do not have any discontinuities. Okay, questions? All right. This last one, we're going to look at ones like this last one in greater detail in another set of notes, but I want to think about this one here because I think it's good to introduce it in this place. All right. We have a piecewise function. They are telling us we want to find the constants a and b such that the function f is continuous for all real values of x. So I've got this, in fact, let me move over here like this. If this was calculator active, it won't be, but if it were, let's just think about this with Desmos. I could type it in. I could do x is less than -2, colon, ax to the second minus b, comma, -2 less than or equal to x less than or equal to x less than or equal to 2, colon, ax plus 2, comma, b, oh no, x greater than 2, comma, b. And I could put me in some sliders here, and it would graph this for me. And then I could, like, mess with these problems, these values here. Oh, gosh. That's an issue, isn't it? Gotta get that to match, but then I gotta get, oh, that would work. That would work. I could get it to match up, right? You can play with them, play with your sliders. there are some numbers for A and B that will make this always continuous, right? It'll make all your pieces match up. They are not going to give you a problem like this on the calculator active section where all you have to do is use sliders on Desmos, because the AP people write the tests knowing that you could just do that there. Let's think about how to do it algebraically. Okay. All three of these pieces, this is a quadratic, this is a line, this is just a horizontal line, right? All three of these pieces are continuous everywhere. You're not going to have discontinuities within the pieces. So that means that your two issues are at -2 and at 2. Okay? So that means the limit as x approaches -2 from the left of f of x has to equal the limit as x approaches -2 from the right of f of x. So we're starting with the -2. Now, I'm going to write this step. That means the limit as x approaches -2 from the left of ax squared minus b. And over here, it means the limit as x approaches -2 from the right of ax plus 2. I got a lot of variables here, right? I need to plug in, just direct substitution to solve this, what number or what variable do I replace with my -2? The x. The a's and the b's stay, okay? So this side right here would be a times -2 squared minus b. Over here, I would have a times -2 plus 2. I could simplify a little bit. -2 squared is 4, so that's going to be 4a minus b equals -2a plus 2. Can I solve that equation and get a number for my answer? I cannot, because I have an a and a b. I can't solve an equation that has two variables in it. I'm kind of stuck right here. I'm going to abandon this and go to +2, and maybe we'll have some luck over there. Okay, so for +2, I'm going to do same thing, limit as x approaches +2 from the left of f of x has to equal the limit as x approaches +2 from the right of f of x. And from the left, so limit as x approaches +2 from the left of ax plus 2. From the left, we'll be looking at ax plus 2. And from the right, we'll be looking at b. Okay? What do I need to do now? When I do that limit, I plug in 2 for x. So over here, that's going to be 2 times a plus 2 equals, what do I get on the right side? Just b. There's no x to plug a number in for, right? So just b. Can I solve that equation and get a number for my answer? Okay. So, who can reach deep, deep, deep into their Math 1 brain and remember how to solve this? Because we're down to a Math 1 problem now. Any ideas on how we could solve this equation? Or solve these equations? Okay? So this is called substitution. B is equal to 2a plus 2. right? Both of these statements are true. So if b is equal to 2a plus 2, that means I can replace it with 2a plus 2 over here. So that would look like this. 4a minus, make sure you put some parentheses here, 2a plus 2 equals negative 2a plus 2. Am I going to be able to solve this equation? All a's, right? I should be able to solve it if it has an answer. It could be no solution, I guess, but I think it's got an answer. So I'm going to distribute that negative. 4a minus 2a minus 2 equals negative 2a plus 2. I'm going to combine my like terms here. So that's 2a minus 2 equals negative 2a plus 2. What do I do after that? Move things to the other side. I would move this positive. I'd make this a plus 2a right here. 4a minus 2 equals 2. Add your 2. 4a equals 4. Divide by your 4. What do we finally get for our a? So there's one part of our answer. We also need a b. We can plug it back into either equation, doesn't matter, but I would pick the 2a plus 2 because it's shorter, right? So I can say 2 times 1 plus 2 is going to equal my b, and that is going to give me 4 for my b. Okay, we're going to do some more of these. I wanted to introduce it to you here. I know especially that like getting all those A's and B's and having to substitute is something that students are going to really struggle with because you did it in Math 1 in 8th grade. So it has been a long time. I don't know that we've used Desmos so stinking much. I don't know that you've actually had to do substitution or elimination like since then. So we will look at more problems like this. This is actually kind of another section, but it's very much related. So I wanted to do one here so that you could see how, oh, we're looking at the limit from the left and the right at that same point. So if it still feels like too much right there, we'll do some more practice with that. Okay, questions? Okay, your assignment is from your book, page 96, 37 through 53 odd, 57 and 58. And let me go look and make sure I didn't give you any crazy, I may have given you some trick that I shouldn't give you yet, so let me look and see. These should be relatively quick because you're just telling me discontinuities and holes. Yeah, you're fine there. And then 57, yes. 58. Yes, you should be okay on these. It does not have one like example 7. I was throwing that one in there just to get us like thinking about that type of problem a little bit. So you got about